So the last lecture that you looked at was identifying the different types of intermolecular forces of attraction. We had London dispersion forces, we had dipole-dipole interactions, we had hydrogen bonding, and then the last one was the ion-ion forces of attraction. And so today what we're going to look at is not only being able to draw structures, but to identify which structure would have a greater melting and boiling point, and intermolecular forces of attraction have a lot to do with that. So we should probably define make some definitions here. Melting generally occurs when energy is added. When energy is added and a solid turns to a liquid. And boiling also occurs when energy is added and a liquid turns to a solid. So what we have to remember is that these processes occur by an increase in energy and that increase in energy allows the molecules to overcome forces of intermolecular attraction. And so that brings us back to talking about the different types of intermolecular forces of attraction. And hopefully you will remember that there was London dispersion forces, which was weaker than dipole-dipole. Which was weaker than hydrogen bonding. Which was weaker than ion-ion. So these would be the weakest, and these would be the strongest. And so what that tells us is that as you go, as you compare molecules in terms of identifying their melting and boiling point strength, the ones that have the stronger types of intermolecular forces of attraction are the ones that are going to have the higher boiling and melting. So here's an example. We have dimethyl ether and a compound called ethanol. Both of these compounds happen to have the same chemical formula, which is C2H6O, but they're different structures, and they are different, and they behave differently. So if I'm going to draw these structures, I would know that I have 1 carbon times 4 valence electrons, so that's 4 valence electrons, and I see that I have 6 hydrogens times 1 valence electron, so that's 6 valence electrons, and I have 1 oxygen times 6 valence electrons, so that's 6 valence electrons, and when I add all that business up, that's 6 and 6 is 12, and 4 is 16 valence electrons to find a home for. I know that because of the way the structure is set up, that the carbons are bonded to the oxygen, and then the hydrogens are bonded elsewhere. So we'll get to that in a second. So here's the carbon, single bonded to an oxygen. So those are my 2 carbons. My oxygen, if you remember correctly, would look something like that. So the oxygen is satisfied. I'm now going to go ahead and add hydrogens to each of the carbons. And so in this case, there'd be a hydrogen here, a hydrogen here, a hydrogen here, 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 and here. So that's the first structure. And the second structure, based on how it's written, I'm going to draw it something like this. So I don't know if you can see this or not, but the way the formula is written is very similar to the way the structure it ends up being in both cases. So the dimethyl ether has the CH3O CH3, and that's how I drew it. And the ethanol has the CH3 CH2 and then the OH, and that's how I drew it. Now, the first thing that we always identify is the type of intermolecular forces of attraction. And so I'm going to go ahead and take the time to identify the types of bonds present, and and that will tell me whether the bonds are polar, and then that helps me to determine whether or not what types of intermolecular forces of attraction this particular molecule would have. So for the first molecule, I have a carbon and a hydrogen. Oops. And a hydrogen. I have a carbon and an oxygen, and that's kind of it. Those are the bonds that are present, I think. So carbon and hydrogen, yeah, that seems about right. So if I was going to go ahead and identify the types of bonds that we have here, carbon has an electronegativity value of 2.5. And hydrogen has an electronegativity value of 2.1. And oxygen has an electronegativity value of 3.5. So when I go to figure this out, 2.5 minus 2.1 is 0.4. So those are nonpolar. And 2.5 minus 3.5 with the absolute value is 1.0, so that is polar. Over here, on the other structure, I have a few different bonds. I still have the carbon and the hydrogen bond, and I have a carbon-carbon bond, and I have a carbon-oxygen bond, and I have an oxygen-hydrogen bond. So this would be carbon-hydrogen and carbon-carbon and carbon-oxygen, and then there's one more, which was oxygen and hydrogen. So those are all the types of bonds that I have. So we already know from before that the carbon-hydrogen bond, that's going to be nonpolar. So here we have nonpolar. Carbon-oxygen is going to be polar. We've already determined that. And carbon minus carbon is 2.5 minus 2.5, which would be 0.0, so that's also non-polar. And then oxygen and hydrogen, oxygen is 3.5, hydrogen is 2.1. So if I figure out the difference there, that's 1.4. Okay, so what this tells me is I do have some dipole. Let's see, so on the structure on the left, the dimethyl ether, that one automatically, no ifs, ands, or buts about it, is going to have LDF. As a matter of fact, both of them will have LDF. But then the other thing that I see present here is I see a polar bond, and that polar bond occurs like here, so this would be slightly negative, this would be slightly positive, so there's some dipole. Now, on the other structure, and I don't see anything else, so on the other structure, I see, again, LDF. I also see that there is polar. So here would be my slightly positive, and here would be my slightly negative, and then I see that it's also polar. So first of all, so that the carbon oxygen would give us the dipole. Ahead of myself, but because of the oxygen bonded with the hydrogen, I also have hydrogen bonding. So I have 3 different intermolecular forces of attraction here versus 2 different intermolecular forces of attraction. And because everything else is the same, I'm going to be able to identify that the ethanol has a higher melting point and boiling point. I don't need to spell it out. You guys can figure that out. Okay. So this one has higher melting point and boiling point because it has stronger intermolecular forces of attraction. But because, look at another example. Here I have CH4 and CH3. So in this case here, this formula is CH4. This one is C2H6. So they're not the same this time, but I'm going to draw the structures. So I see that I have one carbon times 4 valence electrons, which is 4 valence electrons, and 4 hydrogens times 1 valence electron, which is, 4 valence electrons. And when I add that up, I get 8 valence electrons. So when I go to draw this structure, it's carbon with 4 hydrogens around it, and that's going to look just like this. And then on the other structure, I have, 2 carbons times 4 valence electrons, which would give me 8 valence electrons. And I have 6 hydrogens times 1 valence electron, which is 6 valence electrons. And when I add all that up, that's 14 valence electrons. Now, I'm going to draw this structure sort of as it's written. That's kind of how it looks in real life. So it'd be carbon, carbon. I'm going to bond that together. I'm then going to go ahead and bond my hydrogens around like this. Now, I know that the intermolecular forces of attraction in the first one are between carbon and hydrogen. Between carbon and hydrogen. So that would be, carbon is a 2. I forget. I should know this. 2.5. And hydrogen is a 2.1. That one I do know. And I'm going to subtract that, and that gives me 0.4. So that is non-polar. So all 4 bonds are in this structure non-polar. So that tells me that the only type of intermolecular force of attraction that can be present is LDF. Now, the next one, I have carbon and hydrogen, just like before, and I have carbon and carbon. So we know that the carbon and the hydrogen are going to be nonpolar. And because carbon is a 2.5 and bonded to itself is also a 2.5 in the middle there, that gives me 0.0, which is also nonpolar. Now, so that means that that this molecule also will only exhibit London dispersion forces. So how do we determine which one is going to have a greater boiling point or melting point? And the answer to that question is based on the number of electrons. So because remember we talked about London dispersion forces, and the London dispersion forces were the shift of the electrons kind of creating an instantaneous dipole on one side of a nonpolar molecule and the other side of the nonpolar molecule, because the electrons are going back and forth and back and forth. That what that means is that the element or the compound that has the greater number of electrons is going to have the greater instantaneous dipole, which means its force of attraction is going to be larger, which means that it's going to have a higher melting point and boiling point. So more electrons, when you have exactly the same type of intermolecular forces of attraction, mean higher melting point and boiling point. We have one more to go through. This is ethylene glycol and propanol. These two structures both have, C3H246 and O, and this is C3H6 and O. So they're the same. They're just set up differently. So I'm going to draw these structures, but I'm going to first identify the types of, or I'm first going to figure out how many electrons, valence electrons, I need to find a home for. So this one has 3 carbons times 4 valence electrons, which gives me 12 valence electrons. And then I have 6 hydrogens times 1 valence electron, which gives me 6 valence electrons. And then I have 1 oxygen times 6 valence electrons for 6 valence electrons. So when I add all that up, 12 and 6 and 6 is 24 valence electrons to find a home for both of them. Now I'm going to draw these structures again sort of as they look, which says to me that I've oh wait, did I get carried away there? There's 1, 2. Oh, hold on. This 1, 2, 3, 6, 5. So this has to do with that one. So that means I screwed something up on the other one. I only see 2 carbons. So I got to go back and fix that. So let's see. That's 2 carbons. 1, 2, and 1, 2, 3, 4, 5, 6, 6, and 2 oxygens. Oh, there's where the trouble is. So let's go back and identify the correct number of electrons and things, valence electrons. So it's 2 carbons times 4 valence electrons gives me 8 valence electrons, and then I have 6 hydrogens times 1 valence electron for a total of 6 valence electrons, and then I have 2 oxygens times 6 valence electrons, which gives me a total of 12 valence electrons. And then when I add this guy up, 12 and 6 is 18, 18 and 6 is, what is that, 26? Something like that? Yeah, 26 valence electrons. So now I'm going to go back and draw the structure. So when I draw the structure, I know the first one, the carbons are going to be in the middle. And the way that this is drawn tells me my oxygens are going to be on the ends, and then there's going to be at least a hydrogen out here and a hydrogen out here. So let's see, let's connect these all with single bonds. Single, 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 single. And then it looks like I have 2 hydrogens to put a home on each of the carbons. So let's see. Looks something like this. Something doesn't look right here. OH. 2, 4, 6, 8, 10, 12, 14, 16, 18. Oops. Sorry, bear with me. 18, 20, 22, 24. Feel like I'm missing something here. What is wrong? It's an ethylene. Well, let's see. Ethylene glycol. Oh boy. In any case, that structure looks something like that. So it's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I drew it right. We're good. The other one is propanol. Sorry, that took a lot longer than it should have. The other one is propanol, which has 3 carbons together. Single bonded. And then there is an O at the end. And then there is an H at the end of that. And that would look something like this. And then the first hydrogen, or the first carbon has 3 hydrogens, the second carbon has 2 hydrogens, and the third carbon also has 2 hydrogens, which would look like this. And then we would have to add our 1, 2, 3, 4. So let's see, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Did I not math right? Let's see. 3 times 4 is 12. Check. 6 times 3, 4, 5, 6, 7, 8. Wow. You are struggling today, V. So I don't know what's going on here. So this should have been 8. So that should have been 8. So then that should have been 26. 26. There it is. That's much better. Now, many apologies. So, in this case, they both have the same number of valence electrons, and as a result of that, we now need to go through the process of identifying the types of bonds. So, I'm going to start with, there's a carbon-carbon bond, there's a carbon-hydrogen bond, and there's a carbon-oxygen bond. So, let's do this. Carbon-carbon, carbon-hydrogen, and carbon-oxygen. And then there's also an oxygen-hydrogen bond in the first structure. So here. So the carbon-carbons are going to be, let's see, that would be 2.5 minus 2.5. And then there's a 2.5 here and a 2.5 here. So then minus equals 0. And then the carbon-hydrogen would be 2.5 minus 2.1, which is 0.4. 2.5 and oxygen is 3.5. So that would be a 1.0. And then the oxygen and the hydrogen would be 3.5 and 2.1, which would be 1.4. So this is non-polar, polar, and polar. So what I see here in the left structure is I also happen to see the fact that so this would be my polar, so the non-polar stuff is in the middle, and here would be slightly positive, slightly negative, slightly positive, slightly negative, and then I also, so there's some London dispersion forces because of the non-polar part of it. There's some dipole because of the carbon and oxygen, and then I also see that there's hydrogen bonding because of the oxygen hydrogen, and the thing of it is we'll talk about that in a second. Now, over on the other molecule or the other structure, I have again carbon and carbon, which we've already said is nonpolar, and we have carbon and oxygen, and we have carbon and hydrogen, and oxygen and hydrogen. So we have carbon and carbon, which we said is nonpolar because of math. We have carbon and hydrogen, which is also nonpolar. Then we have carbon and oxygen, which we have already identified to be polar. And we have oxygen and hydrogen, which we've also identified to be polar. Now, looking at this, I see that pretty much everything on the left side of this molecule is nonpolar, but I do have a slightly positive and a slightly negative side right here. So a couple of things. I see that I have LDF, I have dipole, and I have hydrogen bonding. And so in this problem, I have the exact same type of intermolecular forces of attraction. I have the exact same type, or the exact same number of valence electrons. But what I don't have the same of is the number of hydrogen bonds. So in this one on the left has hydrogen bonding here and here, whereas on the right, hydrogen bonding only shows up once. So because the ethylene glycol has hydrogen bonding showing up 2 times as compared to the propanol, which has the hydrogen bonding showing up 1 time, that tells me that this structure, the ethylene glycol, is going to have the higher melting point and boiling point. So that's this is the work that's going to be required for you to do this particular type of assignment, and your worksheet is going to have some problems where you are identifying the different whether or not the structures have a higher boiling point or melting point. You are going to have to first of all start by determining the number of valence electrons. You're then going to have to draw each structure. You're then going to have to identify the types of bonds that are present using the electronegativity differences. Then you're going to have to identify the types of intermolecular forces present. Then you'll be able to make a determination as to whether or not which molecule has the greater melting point or boiling point. So good luck with that, and I will post an answer key on Wednesday, as this assignment will be due. No, I'll post an answer key on Friday, as this assignment will be due Friday, I believe. So good luck.